Excellent. So I want to welcome everyone, and I wanted to welcome any guests that we have, but actually we don't have any guests. We have some new members that just joined. So thank you and welcome, and I hope you have a good time. We've got a great program tonight. We're going to jump right into the program with Michael here in just a moment. And then we just have a quick few announcements. Mike and Susie have brought some delicious looking cookies and brownies. They're low calorie, right?
Low calorie. You bake them with fat butter.
No fat butter. Okay. So help yourself to those. And so let me introduce Michal Warzecha. Michael is a friend of the club. He's a member of the club. He's also a member of the Sacramento Club. So this guy gets around. We're humbled to have Michael this evening. Michael is a NASA and JPL solar system ambassador and has a lifelong interest in astronomy and aerospace. At the age of 6, my gosh, he was barely out of diapers, right?
Yeah.
He became fascinated with space by watching live broadcasts of the Apollo-Soyuz test project. That was a joint US and Russia, Soviet test program. He earned his BS in aerospace engineering at the University of Michigan. Does that make you a Wolverine?
Absolutely.
All right. An MS in mechanical engineering at the University of Washington. What's that make you from Washington?
That makes me a husky.
A husky.
Yeah. I'm a Wusky. You know?
A husky and a Wolverine mixed together. Okay.
I couldn't lose during the national championship. You know?
Right. He's a professional engineer with the state of California, licensed mechanical engineering, and he has over 30 years of experience in the engineering field and has worked on the Boeing 777, Artemis, Atlas V, and missile systems. His current job is as an electrical mechanical engineer in the aerospace industry for Northrop Grumman, right? And serves as on the board of directors with the Sacramento Valley's Astronomical Society. So put your hands together and welcome Michal Warzecha.
Thank you, Tim, for that introduction. And it is great to be here. Thank you for the invite. And I'll be happy to show my presentation. Just give me a moment so I can start sharing.
Sure.
Okay.
And let's talk about the photo there with, you've got your
Oh, yes.
signature, and you're in front of what capsule?
That is the Apollo 15 capsule, which was the 4th mission to go to the moon. This is in Dayton, Ohio at the Air Force Museum. And all 3 astronauts that were there were alumni of the University of Michigan.
Oh,
So that's why I have to wear my Michigan swag as in front of the all Michigan crew capsule for Apollo 15. And that was the first mission to take a lunar rover to the moon. So it was a pretty ambitious mission at the time.
Oh, that's right.
Yeah.
Okay. That's a great museum there.
It is an incredible museum. It's probably one of the best aviation museums you'll ever find. And I'm not sharing it. One second.
Looks like Mickey Mouse is peeking out the top.
Yeah, that's part of the recovery system. But yeah, you know what? I won't be able to unsee that now. Okay. Okay, so can my slide be seen now? There we go.
Oh, we can, yeah.
Excellent, thank you. So I'll get out of the way here. So I'm here to talk about James Webb, and I am affiliated with the Space Telescope Science Institute that runs the James Webb and the Hubble. They gave me a slide deck a year and a half, almost 2 years ago, actually, for the 1-year anniversary, or a year ago for the 1-year anniversary. And I've had to significantly add slides because of all the things that I've discovered since last year. And I'll start out with a quote by Carl Sagan, which is that somewhere something incredible is waiting to be known. And that is absolutely true with James Webb. We are discovering stuff that's mind-blowing and changing the textbooks on astrophysics and astronomy. This is just one example. This is a Herberg-Haro protostar. We had a hard time seeing these because they're behind dust. James Webb, of course, penetrates dust, and I'll explain that in a minute. But this is a star that has not started burning nuclear fuel, but is actually shooting out jets of supersonic jets of gas away from itself, and that's caused by gravitational attraction and initial crunching of the star by gravity. This star is only about 8% the mass of the sun, but it'll grow to about the size of our sun. It's only 10,000 years old, and this is what our star looked like, our sun looked like at the very beginnings of our solar system. And these don't last very long. These only last on the order of tens of thousands of years. So it's a real treat to be able to get a snapshot of these with such detail as James Webb has. And there is news every day. So as I was preparing for this meeting, I downloaded this off the internet. This was released today from James Webb. And this is a Digel cloud. It is located on the outskirts of our solar system. And this is a newly formed star cluster. I don't know much about it because, like I said, I pulled it up about 5 minutes ago, and I'll give a link as to where you can see this information online. One thing about this type of a star cluster is because it's 58,000 light years away from the center of the galaxy, we're like 20-some thousand light years away, that these stars are very metal poor. They're mostly hydrogen and helium because the outskirts of our galaxy don't have the heavier elements like the more central or closer regions to the center. So I'll be reading up about this tonight to learn more. So we know that James Webb is an infrared telescope. And the question is, why infrared? There's a common misconception that James Webb replaces Hubble. It does not. It's a complement to Hubble. Hubble is mostly in the visual range, and you can see the, unfortunately, I got a pointer here, but you can see the visible spectrum here. It goes a little bit into UV, a little bit into infrared, but James Webb goes from the near infrared into the mid infrared and covers the right-hand lower wavelength side of the spectrum. And scientists want to, and also one of the reasons that we do image in infrared is because of redshift. Per the Big Bang, our universe is expanding, and the further away an object is, the older it is, because it took that much longer for light to reach us, and the faster it recedes. So the further away, the older the object, the faster it recedes, and the light gets stretched because of Doppler shift. Same concept as a truck going by and you hear the pitch of the truck change. The same thing happens with light. The problem is the really, really old stuff from 13 billion years ago is redshifted so far, the visible part of the spectrum is redshifted into infrared. And James Webb is allowing us to peer much further into that redshift than ever before. So that's one reason. The other reason is dust. And astronomers have a love-hate relationship with dust. This is the awesome Pillars of Creation, or the Eagle Nebula photograph from Hubble, and it's basically in the visible spectrum. Near infrared lets us penetrate these dust clouds. And this image from the near infrared part of the spectrum on James Webb shows you how much more detail we can see in that nebula. Notice all of the stars that suddenly pop into view when we're looking at the near infrared part of the spectrum. And then as we go further into the longer wavelengths, in the mid-infrared, we actually no longer penetrate the dust, but we see details in the dust itself. And again, complementary nature. Astronomers want to see all three of these images because they all give us a different part of the spectrum, and we have a different level of understanding of the phenomenon in this nebula here, which is also a stellar nursery creating new stars. So that, and the pictures are spectacular, and it's neat to see how each picture shows a completely different perspective of the same deep sky object. And one thing about the spectrum is astronomers want to go further than just the infrared and the visual. And I'll give you a quick example. This is the Crab Nebula, and this is a Hubble shot of the Crab Nebula. We're all familiar with it. And this is how it looks in visual. If we go across the spectrum, this is what it looks like in X-ray. This is what it looks like in UV, and these are from the Chandra and the Newton space telescopes. This is what it looks like visually. This is what it looks like in infrared from Spitzer. This is what it looks like in radio from the Very Large Array. And these are artificial colors going from low wavelength violet all the way down to red. So as you can see, a scientist can see so many different details based on which part of the spectrum they're looking at. And when you do a composite picture, this is what you get. So, and it's interesting because I'll talk about the colors in a second. Each color highlights a different part of the spectrum, and you'll be able to see which, which part is radio, which part is infrared, which part is X-ray, et cetera, in that composite image.
Hey, Michael, could you go back a slide?
Sure.
Can you tell us a little bit about what the M1 Crab Nebula is?
Yes, thank you. The M1 Crab Nebula is a remnant of a supernova, and stars that are at least 8 times more massive than our sun explode in spectacular fashion. This happened about 1,000 years ago, and when they explode, they shoot basically like a globe of gas and dust that's being shot out from the point of where the star used to be. And this nebula is ever expanding. So it's expanding over time because of the massive amount of energy that it blasted into space. And these explosions create heavier elements. Supermassive stars create iron. And only supermassive stars that die in a supernova create iron. So the iron in our blood is the remnant, sorry, oh, that's okay, of a supernova. We are made of stardust. So it's a pretty neat thought, because in the Big Bang, only hydrogen, some helium, and a trace of lithium were made. All the heavier elements were created through astrophysics. Am I back online, or?
You are, so we're jump screen.
Okay, that's fine.
We had a problem earlier, so I'm gonna shut.
Sure.
Good time to get a cookie.
Good, there you go. Actually, I'm gonna grab my water.
Hey, leave your money there.
For me, when I'm seeing it, I remember only Avengers, where he comes with all kinds of stones and he talks about nebula and everything.
I love, these are great to see with your eyes too, in the sky. So here's another example of infrared. So here's a Hubble image of the Ring Nebula, M57. It's actually hot towards zenith right now in the night sky. Great thing to look at through a telescope.
Doesn't look like that in my scope.
Yeah, well, you got a much bigger scope with Webb. But you can see a real difference in detail. For example, look at the visual image on the left, and then the near infrared. You can see tendrils of gas and dust that are emanating radially from the nebula. And then, of course, when you look at the mid-infrared, you can see very different details too. So I think these are spectacular images. And also the Ring Nebula is, I believe, a nova remnant, where a smaller star starts shedding waves of gas. Somebody correct me if I'm wrong, but I don't think it was a supernova. I think it was a nova. So our sun will die like this in 4 billion years, where as it's running out of elements to fuse, it starts shedding gas in a bubble. And yes, there's a white dwarf in the center. And I think that's it right there, I believe. Yeah, you need a really big telescope to see that one.
22-inch scope on top of the mountain on a really dark night.
Yeah, with excellent seeing and transparency. And no cataracts, yeah. So I'll talk a little bit about James Webb. James Webb is actually 1 million miles away from Earth. And it is actually in what's called an L2 Lagrange point, or Lagrange point 2. And what it does is it orbits the sun, but it keeps the Earth between the sun and itself. There's lots of reasons for this. One is, and I'll talk about the infrared reasoning for this, but it basically rotates around the sun like a clock hand with the Earth on the hand itself. So infrared. So to be able to photograph infrared, you need your telescope to be really, really cold. And James Webb has a hot side, which always points to the sun, and a cold side, which always points away from the sun. So the hot side has the reaction control jets for any type of maneuvering. It has a communication dish, solar array for power, etc. And the cold side has all the instruments. So the hot side is about 400 Kelvin, where 0 Kelvin is absolute zero. You cannot get any colder than 0 Kelvin because all atomic motion stops. And that's about, the hot side's at about 260 degrees Fahrenheit. The cold side is at 40 Kelvin, or 390 degrees below 0 Fahrenheit. But that's not enough. That'll work for the near infrared instruments. For the mid infrared instruments, there's an active cooler that brings it down to 7 Kelvin, or 447 degrees below 0 Fahrenheit. And this is why it has to be always pointed away from the sun. It can never look back at Earth because you would toast the instruments. So the delta T, or the temperature difference between the hot side and the cold side, is over 700 degrees Fahrenheit. That's amazing engineering to pull off.
Wow.
And this gives you an idea of the size of the primary mirror. Hubble telescope was about 94.5 inches in diameter. Webb is 256 inches in diameter. Palomar, which was the biggest scope for the second half of the 20th century, is 200 inches in diameter. So another statement about the engineering is we basically have a Palomar, bigger than Palomar telescope, 1 million miles away from Earth. And here's just a few stats on the telescope. It's a f-stop of 20, and it has a focal length of 131.4 meters. So that is a gargantuan focal length. And the launch mass was 14,300 pounds. Actually, that's not that bad as far as launch weight. So not only does it take photographs, but it also takes spectra. And I'll be addressing some of the spectra analysis that's done. But a spectrograph is basically the same thing as a prism breaking up light from a star or the sun or whatnot. A rainbow is actually a natural spectrograph. So you're looking at the electromagnetic spectrum, across various frequencies. And with that, you can actually detect elements and molecules in the spectrograph. So this is a spectrum of a galaxy that's 13.1 billion light years away. And in the spectral analysis from Webb, they're finding oxygen, hydrogen, and neon in that galaxy. And it's got 4 main instruments. It has a near-infrared spectrograph, near-infrared camera, mid-infrared camera, and spectrograph, as well as a FGS NIRISS, which is a slitless spectrograph, which is a really complicated instrument that I'm not quite sure I understand, but it does also spectroscopy. And the spectroscopy is just as important as the photographs. So with regards to the photographs, this is the mid-infrared filter wheel. Space probes do not use color cameras. It's a lot like what imagers do. They take an image in black and white, and they'll take multiple images through various filters to create a composite image. And if you were, let's say, doing this in visible light, and astrophotographers obviously know this, you would take a picture through the 3 primary colors, red, green, blue, and then composite the image together to get a true color photograph. Same thing with the infrared photography. And I need to find out how much this filter will cost, because I'm really curious. And this is the near infrared camera filters. So you can see they've got different bandwidths and different slices of the spectrum. And typically, we as human beings cannot see infrared light. So the colors that you see on any Webb photograph are artificial, because unless you're a snake, you can't tell us what the color is. So they'll assign from the short wavelengths, they'll begin with the blue part of the visual spectrum to assign colors all the way to the red. So generally when you see a Webb picture, if you see a red color, that means that it's on the long wavelength side of infrared. If you go towards the blue, it's on the shorter side. Now they make exceptions for that, but this is generally how they do assign colors. And this is the filter pack for the mid-infrared. So any astro imagers might be interested in looking at this. I'm a visual guy. I don't do astrophotography. So if anybody has any interesting tidbits on this, I'd love to hear it. So Webb's discoveries. This is, again, going back to the pillars of creation. And this is actually a composite picture of near and mid-infrared images. So this is a pretty broad spectrum infrared shot of it. And I think it is spectacular. Because you can see, not only can you see all the stars that pop out in the near infrared because we're penetrating dust, but you also see the dust details from the mid infrared. So you're seeing the best of both worlds in this really spectacular image. Now, I'll start out with the solar system, because Webb also looks at our planets. The closest planet it can do is Mars, and not very well because it's too bright. But it cannot look at the inner planets or Earth, again, because it would point towards the sun and burn out its instruments. But to give you a perspective, this is Jupiter taken through, I think this was Hubble. Yes, Hubble. This is a Hubble image of Jupiter. And this is an infrared image through Webb. One thing it does allow us to do is actually penetrate some of the cloud details. And when you look at that picture on the left, if you look at the very top, that red line there is Aurora Borealis, or Northern Lights on Jupiter. To give a size perspective, in the bottom right-hand corner with the little insert around it is the Great Red Spot. And you could fit like a couple of Earths across that spot. Is it like 2 or 3 Earths? So that gives you an idea of how strong and huge those auroras are. And then on the right side, which is a magnification of the Great Red Spot, and this is where they make an exception on the color palette, this is showing the Great Red Spot storm in infrared. And the red clouds are the high altitude clouds, and the blue is the lower altitude storm of the Great Red Spot. And we don't quite understand the Great Red Spot. We're still trying to learn the dynamics of how that thing works. And this is actually helping us do that. This is Saturn. I think this might be Cassini. I actually don't have a detail on here. This is visible light, and this is Saturn in infrared. Now, one thing that James Webb with infrared does is makes things very different. The methane gases on Saturn tend to absorb some of the infrared, but the rings, because they're ice particles, pop in infrared. And notice how much brighter the rings are in infrared versus the main body of the planet. And the same thing with Uranus. Uranus has rings. We cannot see them from Earth in the visible spectrum, but notice how the rings just pop beautifully in infrared. And I always love these. Notice when you look at the photographs of photobombing, look at all the galaxies, the distant galaxies that are being picked up at the same time. And you'll notice that on many of the photographs. And Neptune as well, in infrared light, has the same phenomenon. Neptune has a very thin ring system that we can't see from Earth either. But again, infrared, that ring system just pops. And that bright object in the upper center of the image is not a star. That's Neptune's moon, Triton. Triton is covered in nitrogen ice, and that just reflects infrared light like crazy. It's even brighter than the planet, which is actually not true in the visual spectrum. And also some discoveries. This was a new thing they found a couple of years ago. Enceladus has water geysers, and Enceladus is dumping like just gallons and gallons of water every second as it orbits Saturn. And what they discovered is all that water has been accumulating in like a aqua ring around Saturn itself. We didn't know about this until we saw the infrared image where it shows a little inset there that shows a pixel of Enceladus and the plume of water coming off of its geysers. So this is a really neat discovery, and the planetary scientists love this telescope. Yes, yes. Now the density, of course, is not very high because it's in space in a vacuum, but there is like a water ring around Saturn that we did not know about, caused by Enceladus basically having these eruptions of water from its geysers. And that's, again, that's the magic of infrared, because we can see stuff that our eyes can't see. Also, this is an image of Titan, Saturn's biggest moon and the second biggest moon in the solar system. Titan has an atmosphere of hydrocarbons. You could mine fuel from its atmosphere. They're actually picking up weather patterns on the atmosphere of Saturn. So this is only about 40 pixels in diameter. So a planetary moon is very, very small in the sky. And yet, even with that very small size of the moon, we can actually see weather patterns. So exoplanets. Exoplanets are planets that are orbiting stars other than our sun. And over the last few decades, we discovered something north of 5,000 exoplanets around other stars. When you look up at the sky at night and you're seeing stars, almost all those stars have exoplanets. There are more planets in our galaxy than there are stars, is what scientists think. And going back to stars, I'll talk about exoplanets in a minute. This is another one of those stellar births. This is a star that, again, is freshly born, and it's shooting jets of gas and plasma to the top and bottom of the screen. When you look at the center of the screen, you can see a little accretion disk actually going through the center of this hourglass, that is eventually where a planetary solar system will form. And again, this is what our sun looked like 4 billion years ago. Now, this is near infrared. This was shot in 2003. And recently, they pointed the mid-infrared camera and notice the difference in what you can see. So that's mid-infrared. So you get very different details on this object, just moving across the spectrum. And it's pretty cool, you know, how you can see just a very different perspective. You see a little bit of commonality, but in general, it's just a whole different part of the gas cloud that's coming out of the star that's visible. Going back to exoplanets, we've discovered about 5,000 exoplanets, and that's usually what they do is they use what's called a transient method, where the planet goes in front of the star and the light dips in the star, and they can detect the planet that way. Or they use what's called a Doppler method, because when a planet orbits a star, it causes the star to wobble a little bit, and that light will shift slightly in frequency from the star. And using incredible mathematics, they figure out the orbit and general size of the planet. Webb is not the only telescope doing this, but Webb is actually directly taking photographs of exoplanets now. This is Epsilon Indi AB. It's only about, I think, 12 light years away, I believe. It's several times as massive as Jupiter, and it's one of the coldest exoplanets observed so far at about 2 degrees Celsius. And I think it has like a 40-year orbit around its parent star versus Jupiter, which has 12. And this star is about 3/4 the size of our sun. To take this image, they have to use an obscuring mat, and that where that little star is, that's where this parent star would be, but they have to obscure it when they image it, otherwise it would blow out the image. And I think it's pretty awesome to be able to see an alien planet.
Have they yet been able to detect exomoons?
No, not as far as I know, no, not yet. I hope to be proven wrong tomorrow, but not yet. And going back to star formation, I love this image. This is NGC 1333, and this is showing details of stars being born. In the life of a star, you have a nebula which provides the material to build a star. Gases coalesce. Eventually, the star becomes those protostars, and then starts generating nuclear fusion. So you can see some of the gas cloud details here in this nebula forming stars, and you can see bright stars that are forming an open cluster that are birthed by this nebula. And our sun began like this, again, 4 or 5 billion years ago, and our sun was also part of an open cluster like you see here, though the siblings of our sun have been scattered around the galaxy as we go around the galaxy because of gravity. So we probably have sister stars that are on the other side of the galaxy right now. And going back to supernova, we are discovering never before seen details in supernova structure. And again, a supernova is a star that's 8 or more times bigger than our sun. When it no longer can produce energy through nuclear fusion, it explodes extremely violently. This is one of the most violent things you can see in the universe. And as I said, these gas clouds create the heavier elements that we have in our bodies or all around us. And with, again, like the mid-infrared imaging, which pops the details in these clouds, we're learning more about how these supernova happen and what they create. Horsehead Nebula, spectacular deep sky object in Orion. And I love this picture because the left side is from the European Euclid telescope, which is visible in infrared. Center is Hubble, and again, Hubble has a very small sliver of infrared. And then the right photograph is Webb in infrared, where you can see lots of details in the very top of the cloud. So we're getting more data as far as how these nebulas behave. And going back to photobombing, notice more photobombs. It's got all these galaxies that are infiltrating the photograph. So one of the questions is, where do some of our heavier molecules come in on Earth? Where does some of our water come in, our silicates and other things? A lot of those elements and molecules are formed in cold ice clouds. And the best way to see cold ice clouds is, again, with infrared. So we're learning about some of the evolution of where materials came into our solar system through this kind of observations. And this is a very cold ice cloud. I believe it's in the southern hemisphere, the Camelonia 1. And I think it's a very beautiful photograph. And it's also definitely towards the near side of infrared with the blue haze. One thing about penetrating dust, James Webb does penetrate dust very well, but at some point the dust is so thick, it can't do that anymore. So this is one of those cases, even though it's shot in infrared, the dust is just too thick for it to completely penetrate this cloud. And just going by with more nebula, this is a near infrared shot of the Serpentines Nebula, HBC 672. And to give you an idea of the size, there's a scale up there in light years. And again, this is another stellar nursery where you can see stars being born in this nebula. And you can see all sorts of different details across the spectrum. And again, bear in mind with the spectral assignment, if you're looking at blue, that's closer to visual light. The red is when you're going into further infrared light towards the end of the mid-infrared range. And this gives you an idea of the frequencies of the light coming out. It's neat to see this from the naturalistic beautiful standpoint, but it's also interesting to think about the scientific aspect as far as, oh, what wavelengths are coming out here? And then scientists looking at those wavelengths can better understand what's going on, what the composition is, and what the dynamics is of such nebulas like this. Sure.
Does the wavelength of the light correlate to temperature in some ways?
Yes, it can, yes.
Is it correct, or is it just mostly?
It pretty much is, because if you think about it, if you think about like a star, like on the Hertzsprung-Russell diagram, the hotter they are, right.
Assuming go that way, so that I just.
Yeah, no.
Sure, we're talking about wavelengths of atoms.
Yeah. Generally it does. Now, and redshift, of course, is a whole different ballgame.
What's that?
Redshift is a whole different ballgame. Yeah,
But basically on stuff like this.
yeah.
It's colder and the warmer sections in the middle there.
Yeah. And again, they might make exceptions as far as color assignments too. So they generally do the blue to red assignment, but it's not always true. They might pop a color to see like hydrogen alpha or some other detail. So, and then if you ever pull the images, you can see here's the filters on the bottom where it says near cam filters, and then they'll assign colors to it. So again, going to this, anybody recognize this object?
The whale?
The what?
Is it the whale?
The porpoise or the penguin nebula, or galaxy rather, excuse me.
I thought it might be the whale.
I think that might be it too. I know it's like a
Well, it
multiple
might be
name.
the one above.
Okay, you're right. So this is a galaxy here, and this is a visible shot. Now, what's interesting is you can see dust lanes in the galaxy itself. When you go to near infrared, you're penetrating the dust and you're seeing more detail inside the galaxy. And notice the little elliptical galaxy here. When you switch to infrared, you're seeing a lot more of the center of the galaxy versus this obscured by dust on the left-hand side. Same thing with the galaxy up there on the right. Now, when you go into mid-infrared, it's a whole different ballgame. Yeah. And one thing about mid-infrared in this case is it tends to look at older stars. So and typically like old stars are cooler. So when you look at the mid-infrared here, you're looking at this elliptical galaxy on the left-hand side of each image, and notice how much smaller it is. So you're seeing more of the older stars in that elliptical galaxy there. The whale that we discussed in the upper right-hand corner almost completely disappears. And again, this is how just by looking at different parts of spectrum, you can gather really good data.
It disappears because there's no dust in it?
It could be the fact that in mid-infrared it obscures dust, but it could be that it's a younger galaxy. So you don't have as many old stars. Yeah. And if you pull this up, there's a whole like long article talking about all those aspects. So, Now, we live in kind of the outskirts, not really the outskirts, but we're away from the center of our galaxy in the Milky Way. We're kind of in the suburbs, we're, I don't know, imagine we're kind of a Stockton, all right? the center of our galaxy is like San Francisco, bustling, active, and whatnot. As awesome as San Francisco is, and as awesome as the center of our galaxy is, you would not want to live in the center of our galaxy because there's tons of stuff that's going to kill you. All right. It's good to be living in the suburbs. So if you look at this image, this is over 500,000 stars. It's pointed at Sagittarius C, which is the center of our galaxy. And when you put some details on this picture, the red lines are needle-like structures of galactic wind, like solar wind, that's blasting through the center of our galaxy. That protostar cluster circled in orange is generating stars, but it's not generating these mild-mannered, dwarf stars like our sun. It's creating giant stars, which explode in a few million years. So you would not want to hang out by that cluster. It's going to be a very dangerous place. There's clouds of ionized hydrogen. There's infrared dark clouds that obscure stuff. So lots of really neat activity to watch from afar at the center of our galaxy. But yeah, you wouldn't want to live there. You would not last very long.
There's a nasty black hole there too.
Oh, that's right. There's a massive black hole there. Exactly. One of the things that we're trying to figure out is dark matter and dark energy. And a friend of mine who's an astrophysicist said, if you understand dark matter and dark energy, you don't understand dark matter and dark energy. And that's certainly true. I can't even begin to understand. To me, it's like black magic. But anyway, over 90% of the matter and energy in the universe is dark matter, dark energy. One of the ways that we try to understand it is by looking at how galaxies rotate. And that's part of the reason that they're discover the concept of dark matter, dark energy is the galaxies don't rotate like we expect them to do. So looking at mid-infrared, we can see dust clouds in these distant galaxies. Actually, this is a galaxy in our neighborhood. And looking at the dust clouds and the patterns that they create can help us try to understand dark matter, dark energy. And again, you wouldn't see this type of work in visual light. Another thing that we're trying to understand is formation of stars, as we saw before. This is M82, spectacular object to see visually in Ursa Major. If you got a Dobsonian, take a gander at it. Our galaxies go through what's called starbursts, where for several reasons, there's a burst of star formation. And in this Hubble image of M82, where the little square is, you're looking at the center of the galaxy and you can't see much because of the dust lanes. But when they pointed Webb at it, it showed many, 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 probably hundreds of thousands of stars being born. And all those little dots are new stars. And those red lines are basically jets of galactic wind that are blowing through the center of that region. So all galaxies go through this for various reasons. And again, we're learning about how stars form. And there's a little key there at the red. The green is actually iron, and the red is the galactic wind and hydrogen. I wish I was an astrophysicist to talk about this more, but this is about as far as I can go. So one of the neat things about Webb is doing deep fields. Hubble did this a few decades ago, where the scientists asked to point at a random spot in the sky, and I think the area was like looking through a soda straw. They took a multi-day image. They had to really push to do it because they would say, you can see nothing. Well, Hubble saw a deep field like this, where they saw galaxy after galaxy. Webb is able to do this much faster than Hubble. And Webb is continuing the effort of doing deep field images like this. I recommend you go online, because all this information is public domain, and download a raw image of a deep field, either from Hubble or Webb, because all of those points, except for a few points of light, which are local stars, every point of light in there is a galaxy. And when you pull up a raw, like many megabyte image and zoom in, you'll start seeing these tiny little galaxies all throughout this image. What we're discovering is there's a lot more galaxies than we ever thought possible in our universe. And we keep pushing, from millions to billions, and maybe even at some point, trillions of galaxies in our universe. And that is just mind-blowing. This image right here has about 100,000 galaxies scattered in it, if you were to look closely, which is just insane.
I think though too, they also thought that where they were pointing it at was just gonna be completely black.
Yeah, they did.
They were surprised to find.
They were. And I can just imagine a conversation with the time, because, you know, a space telescope, you've got, you know, 10 times the scientists wanting a slot of time than is available. So I can just see the director like, you know what, this, you know, I've got this guy wants to do this and this experiment. Why, we're not going to do it. And finally, thankfully begged him to do it. And they were just shocked at what they saw.
I think they probably learned from Carl Sagan, pale blue dot.
Yep.
Just try it.
Just try it. Exactly. Exactly. You'll, like I said, there's wonderful things waiting to be discovered. Black hole mergers. This is a black hole merger of the very distant past in our universe. This was 740 million years after the Big Bang. And, oh, I got a mistake there. It says the Big Band. Oh, well, anyway. Autocorrect, love it. So these two black holes that are merging here are on the order of several million solar masses. And one of the things they're trying to understand about the early universe is what role did black holes play in formations of galaxies? And there's a whole debate about galaxy formation going on right now. So, you know, there's a myth that James Webb has, you know, destroyed the Big Bang. It has not. However, you know, in the first several 100 million years of our universe, we kind of didn't quite understand the dynamics of how things were, how galaxies and other things were forming. So Webb is opening up that door, and this is part of opening up that door. It's understanding how some of these early black holes actually behaved after the Big Bang. Also, star cluster formation. This is a shot of star clusters forming in a galaxy 460 million years after the Big Bang. So part of what we're trying to understand is how did the early stars, before we had all the metals formed, and what I mean by metals formed is when the Big Bang happened, all we got was hydrogen, helium, and a little bit of lithium. So the first stars in the universe didn't have any heavy elements in them. So when the stars died and created the heavier elements, the next subsequent generations of stars had different dynamics because the metals were contained in the stars from the previous generations. We have not seen the first generation of stars yet. That's called a population 3 star. I asked the scientists at the Telescope Institute, are we ever going to see a first generation star with Webb? She said, probably not. We might see a supernova, but probably not a first generation star. So my response was, so you're saying there's a chance? But probably not. But you know what? You know, stranger things have happened. So if we could see one of those first generation stars after the Big Bang, that would be like that would be the holy grail in cosmology. One of the problems is those stars were likely very, very massive. And the bigger the star is, the shorter its life. If you get a star that's several times bigger than the sun, or maybe dozens of times bigger than their sun, they're only going to live a few million years. Our sun is like I said, a dwarf star is going to live for about 9 billion years. If you look at like red dwarfs, those will last probably tens of billions of years because the smaller stars are cooler and they burn through their fuel a lot slower than a massive star like the first generation stars. So that's, they think, one of the reasons we haven't seen first generation stars yet. But again, I'm crossing my fingers that we'll spot one. Albert Einstein came up with some pretty neat things. And so far, all the stuff that he imagined has becoming true. One thing that came out of his theories of relativity and whatnot is what's called gravitational lensing. If you have, on the left-hand side, you can see a distant galaxy, which shows a number 1 there. On the right-hand side, you see a number 3, which is the Milky Way. In between us and that galaxy is a cluster of galaxies. That cluster of galaxies has a massive gravitational field, and that acts like basically a telescope lens. So what it'll do is it'll refract the light like a lens, and it'll actually magnify that galaxy behind that cluster. And this is what it looks like. If you ever look at some of the distant photographs that Webb takes, you will see these features, and they look really strange. Those are gravitationally lensed galaxies. So what's allowing us to do is, now the galaxy is very distorted, but this galaxy here is, I can't remember the distance of it, but it's a very old distant galaxy. And you can actually see circles of supernova in that galaxy. And what they're thinking is, because when you look at the gravitational lensing, that the paths in the refraction all vary a little bit. It's not a perfect lens. So what may happen is they'll see a supernova and then trying to figure out a slightly longer path, they'll say, oh, in 20 years, we'll see it again. Because you'll see light from the supernova coming along a different refracted path that's a little bit longer. So this might be an incredible way of gathering ancient supernova data. So we keep breaking the record of the most distant galaxy. And right now, this is the current record holder at 280 million years after the Big Bang. This data is not yet peer reviewed, so it's preliminary. But Hubble could only see about 500, 600 years after the Big Bang. Webb is pushing beyond 30 million years after the Big Bang. We've gone from seeing just maybe a couple galaxies in that region to dozens and dozens and dozens, and we're growing the numbers. So this right now is the candidate for the oldest seen galaxy pending peer review at 280 million years after the Big Bang. So if you ever study redshift, it has a redshift of 14.3. That's a pretty massive redshift. You're really pushing the limits as far as being able to see in the light spectrum. This galaxy is actually small. It's only about 1,600 light years across. And one of the debates is, black holes versus stars. And what they discovered with this thing is, at first they thought maybe there's going to be lots of black holes, but this galaxy actually has most of its light made by young new stars. And it's hundreds of millions of solar masses in size. So it's a fairly compact galaxy. So, so the question is, why is this bright galaxy existing so early in the Big Bang, after the Big Bang? And that's one of the things that has been kind of confusing scientists based on the initial theories we had is we've had brighter galaxies forming faster than we thought. And there's a whole argument going on as to why. So, there's a lot of yelling at each other in the astrophysics community trying to figure this out. And that's a good thing. That's what scientists are supposed to do. So stay tuned. And what they found is that there's probably been several generations of stars in this galaxy, and there's oxygen, which I think was a bit of a surprise too. So the cosmic dawn of the first few 100 million years is not unfolding quite like they expected. But the thing is, when we were doing our initial assessments before Webb, we didn't have a lot of data. So we really were kind of guessing as far as what happened in this time period. And now we're finally lifting the veil and finding out what happened in the first few 100 million years of our universe. And this is a spectrograph of the galaxy. So this shows how they tended to figure out the redshift. There's a thing called the Lyman alpha break where light can no longer penetrate neutral hydrogen. And that break is often used to figure out a redshift. So if anybody's a physicist here, they can probably go into more details on this. But that break is a common way of saying, there's our marker. How much is it shifted towards the red? And that's how they get the 14.3 redshift and then dating the galaxy to be 280 million years after the Big Bang. Peer review pending. So again, going back to galaxy evolution, that's one of the key things that Webb is doing. Here's another view of the Pandora cluster. And when you look at this view, you can also see what looks like some gravitational lensing going on. If you look towards the bottom right, where you have two stars in a row, it looks like you're getting gravitational lensing. So again, it's worth your while to pull up some of these many megabyte images and just peruse them at your leisure, because you'll find all sorts of neat details in these. So one of the things about the early universe is we had neutral hydrogen and throughout the universe, and neutral hydrogen, as I mentioned, blocks light. Over the first few 100 million years, the hydrogen was ionized and let light pass. And we're trying to figure out how that happened exactly. And we're thinking it was early dwarf galaxies. And some of those galaxies were 4 times better at ionization than we thought. So again, that's another process that we're trying to learn as far as the early universe. So much is being learned about this dark period before we could have light penetrating this neutral hydrogen.
Like, wouldn't those early galaxies be populated with a whole bunch of those huge massive stars that are throwing off just incredible amounts of UV
Yep,
and X-rays, and that would cause
yes,
ionization?
yes. Now, the key question is, you know, how big were they? What were the, you know, what were the subsequent generations? All that good stuff. So you're right. So yes, you're getting pounded with broad DC to daylight energy levels coming off some of those objects. But now the question is all the subtleties as to all the details. And like they were saying that we're discovering that some of these galaxies were 4 times better at ionization than we thought possible.
Wouldn't, and we should be able to tell the temperatures of these stars by the redshift.
Right.
And knowing where the most amount of the light coming from, what wavelength it started out, right?
Right, right. So again, endless galaxies pop into view. And again, this is looking back at Pandora. And like I said, you can see what looks like gravitational lensing on the bottom right there. We all know about the crisis in cosmology. One of the ways we measure the expansion of the universe is what's called a ladder method. So we look at, you know, let's say parallax of stars in our neighborhood to figure out their distances. We look at Cepheid variables. We look at supernova, because Cepheid variables and supernova have a known amount of light that they send out. So we will look at those objects like a type 1a supernova or a Cepheid variable. We can say, oh, that's supposed to be this bright, but when I record it, it's this much dimmer, and I can measure the distance between them. There's also another method called the cosmic background microwave radiation. This is the echo of the Big Bang in microwave. And this is an echo from the Big Bang, or 300,000 years after the Big Bang. So that's also used to measure how quickly the universe is expanding. There's another method that we're trying, which is called gravitational wave, but we haven't been able to get that precisely yet. But the problem is, if we look at those Cepheid and other variables in the ladder method, we get an expansion rate that's like 70 some, you know, kilometers per second per megaparsec. We look at the cosmic background radiation, it's slower, like in the high 60s. And if you notice, the error bars do not overlap. And we don't know why. They should overlap. So the question is, who's wrong? Is it the cosmic background radiation, or is it the ladder method? Well, the problem is the cosmic background radiation is well known. And Webb is actually finding out that the ladder method is also working quite well. So, you know, we're not able to answer the question yet. There's hope with this one. They're looking at data from Hubble and Webb to try to figure out more of these ladder method stars to try to bridge the gap. Some scientists are saying we may have done it, but again, there has to be a lot of peer review and yelling between scientists before they finally come to a conclusion on this. But Webb is trying to solve the Hubble tension as well. So hopefully in the next few years, we'll be able to pull that off. And this is only the beginning. We've just scratched the surface as far as the life of Webb. It was launched on Christmas Day in 2021, I think at like 4 or 5 in the morning. And I told my wife, I'm getting up and watching it. And I watched it. She thought I was crazy, but that's okay. So I sat up with my cat watching nervously this thing take off. The telescope itself cost about $10 billion. And it was a partnership between us, the Canadian Space Agency, and the European Space Agency. The Europeans provided the launch vehicle, which was an Ariane 5. And they get a chunk of the telescope time. I think it's on the order of like 13 or 16%. And I'll tell you why they deserve more. The original plan was for a mission of at least 5 years. The main limitation is, remember that L2, that thing. It's not a perfect point of neutral gravity. They have to use fuel to stay in orbit. And it actually does what's called a halo orbit, rotates in this nice halo orbit around that line going to the sun. That consumes fuel. The rocket got it close to L2, and then Webb had to use some of its maneuvering fuel to make that last leap to get into L2. So they budgeted a good chunk of that fuel for that purpose. Well, the Europeans did a fantastic job. They so nailed the orbit that Webb used a lot less maneuvering fuel to get to station than they thought originally was going to happen. So I really tip my hat off to ESA and their engineers, because God bless them, they did a miraculous job. They're predicting that with this extra fuel, they might be able to push Webb's life to 20 years. They know they'll probably get at least 10 years and maybe even another decade after that. So, like I said, they deserve that time, and should probably give them a bonus for what they pulled off. And so we're going to keep learning about the early universe, galaxies over time, stellar life cycles, other worlds. And it's amazing what we're discovering. And one thing I do want to add is, it's wonderful to look at these pictures as an amateur scientist or as a real scientist. It's great to learn about the science behind what's going on in the universe. But one thing we also should do is look at just the sheer naturalistic beauty of some of these images. Because, I mean, this is nature. This is just like going out to Yosemite and staring at the granite walls of Yosemite. This is the Carina Nebula, and I think this is a spectacular photograph. So if you ever look at these pictures, like I said, study the science, but also just absorb the beauty of nature and our universe in seeing these. You know, as Ralph Waldo Emerson said, the sky is the ultimate gallery just above us. And ultimately, me as an astronomer, that's what I love the most about astronomy, is getting my telescope, looking at an object and just staring at it and just absorbing the beauty of it. So, like in that movie, you know, keep looking up. So I will be happy to answer questions. But one thing I want to do is I want to put this page up, so if anybody wants to screenshot it. Don't believe everything you see in the news about James Webb, because there's a lot of clickbait headlines that are absolute garbage. Go to a reputable source. First one on the upper left is the Space Telescope Science Institute. They do regular releases of images. If you're interested in astrophysics, Dr. Becky is a PhD out of the UK. She talks about not just Webb, but other aspects of astrophysics. So she's up here, you know, we're down here, and she does a really good job of bridging that gap. She does an excellent, I highly recommend her. Go to nasa.gov. They have the James Webb mission here. They also have lots of the other missions that are going on, as well as the classical missions like Apollo. And that, you know, I spent a lot of time there. So, and then finally, ESA, you know, the awesome European engineers also have a James Webb website. So I'll leave this up while I'm answering questions. So take a screenshot, and by all means, go down this rabbit hole, please. You won't regret the hours you spend being, you know, looking into this.
Thank you, Michael.
Yeah. So
Okay.
I'm happy to answer questions, or if anybody had a question online, or.
Does anybody on Zoom have any questions for Michael?
If you have a question, I'll
Yeah.
pass the microphone to you, but
And if anybody in Zoom, if you want to ask a question, it looks like you're all muted, so you need to unmute yourself.
Yeah, and I will try my best to answer. I'm not an astrophysicist. The worst thing I'll say is I don't know. So,
Michael, I'll start the questions off with, you talked about the Webb looking at exoplanets.
right.
And identifying them visually in infrared. They're also obviously going to be using spectroscopy
Yes.
to study the atmosphere and to look for life. Would you care to comment on any of that aspect?
Yes, I would. I'd be happy to. They are detecting molecules on exoplanets, including methane and other types of molecules. There is a possibility that we may discover a molecule that we don't have an inorganic method to create that molecule. There was a year ago a researcher that claimed that they found a molecule that's only created by algae. But the problem was statistically that data was really weak. And it was probably an echo of methane, which can be produced without life. But it's a tantalizing hint of what is possible. So we might find a biosignature. The other thing that would be interesting is imagine if you found a chlorofluorocarbon on an exoplanet. So stay tuned. That there is a possibility that they could find a signature at some point. But we haven't seen one that's been definitive yet. We had a hint with that one exoplanet, but again, the data was just too muddy to claim it as a hit.
Help me make the connection here. If we saw a fluorocarbon, that would be an indication of
Industrial pollution.
civilization.
Yes, thank you.
right?
Yes, yes.
Yeah,
Because
mankind.
chlorofluorocarbons were what we put on aerosols in the 60s and 70s, and they eat up the ozone because they float up in the atmosphere and eat up the ozone. So if we saw a chlorofluorocarbon, there's not likely any natural way of producing it. So that would be big news because it's saying, wait a minute, we may have found an industrial civilization. Because the laws of chemistry and physics are the same throughout the universe. So it's likely that an alien civilization will find nuclear weapons, chemical processes, et cetera, because the laws of physics are the same. So yeah, so if we saw a massive plutonium signature on a Earth-sized planet,
Not a good sign.
not a good sign. No.
Warning plus.
Exactly. Tread carefully, humans. So more questions. Happy to, yeah.
So, after the James Webb Telescope was inside the L2 orbit, does it still need fuel to stay in the L2 orbit?
Yes, excellent question. Yes, it does. It needs maneuvering fuel every once in a while to stay in orbit because, if you think about it, if you've got all the other planets tugging, our orbit's elliptical, so there's lots of little minor forces that can kind of disrupt its orbit. So it has to burn fuel to do that. And the Europeans saved us a ton of fuel to keep doing that for hopefully 20 years.
Think of it as a whole bunch of little waves moving
Yeah.
around, and so it's got to kind of push itself back and forth, back down.
Yeah.
a little bit.
Yeah, it's like driving on the road and all of a sudden you hit a little bump and okay, I gotta correct. Oh, big pothole. Oh, I gotta really correct.
Do you know what the likelihood of it will be when it runs out of fuel, where it will go?
Okay, what's going to happen is there's other satellites in that Lagrange 2 area. So what they're going to do is they're going to actually use the last bit of fuel to likely deorbit it. So it'll leave L2 and stay in a solar orbit. So it'll just be going around the sun for perpetuity. But yeah, they do not want to leave it in L2 when it finally ends its mission because it could be a collision hazard.
Okay, so they'll move it before then.
They'll move before then, right?
Hopefully there's no collisions before that.
Yeah, there's, it did get hit. It did get hit by a micrometeorite. Yeah. And it like a little, yeah, it little bit, it like misaligned one of the mirrors. But one of the details that's interesting is, I think they learned this from Hubble. These mirrors have 7 actuators that just really precisely point those mirrors. So with the actuators, they pretty much fix the damage. I think they lost a few percent, but yeah. And one other thing I want to point out, there's a neat thing about space exploration that we get a lot of this technology back into our lives. These mirrors are made out of beryllium, and they're coated with about 1,000 atoms of gold. And the reason they have this really tiny layer of gold is gold reflects infrared light really well. That's why it's a gold mirror. That's literal gold. If you took all that gold, it would have the mass of a golf ball. That's how thin that layer is, which makes sense because in aerospace, weight is your biggest enemy. So yeah, you need gold. So the engineers are like, make it as thin as possible. You need a whole bunch. No, exactly.
Is that why they didn't encase it? Because of the weight and size?
Yeah.
Like Hubble, they encased it?
The case, yeah, exactly, the weight and size. For every ounce, you're taking an ounce off of a scientific instrument or an ounce of fuel life. But the thing is, when they were designing this, they had to get very precise instruments to measure the contours of those mirrors. And they actually developed new ways of measuring that. That technology now is coming into the medical profession. They're using that technology developed from Webb to do retinal scans for eye patients. So they're going to have new technology that'll be a lot better at diagnosing eye diseases because they can now so much more precisely measure the retinal surface of our eyes. And that's all thanks to Webb. And the space program is full of those spinoffs. You know, this is the great grandson of the Apollo guidance computer. So, more questions? Yeah,
I don't have a question. This is Neil here. Just wanted to toss in, hello to everybody. Glad you
hello.
know I'm doing fine as probably the oldest member of the club. I turned 60 just a couple of days ago. I turned 90 years old. And I've been a member of the club for about
3,000 years.
Oh, I think we lost you, Neil.
other comment. I want
Hey, Neil, I'm sorry, we missed your previous comment. Could you repeat it, please? I think your microphone's muting out.
and you missed a complaint, you say?
Yes,
Uh,
yes, please repeat it.
I was just commenting that I just turned 90 years old 2 days ago.
Happy birthday.
Thank you very kindly. And my second comment was that I did watch that program that's shown below on your screen on the James Webb Space Telescope that comes from NASA.
Yep, good stuff online. It's incredible what information we have. Like I said, all the photographs are public domain. And if when I was a kid, after watching Apollo Soyuz, if I had this technology, I never would have left my room. So thank you. Do you have any questions, Neil?
No questions. I thought this was a nice presentation. You put it together in a very thoughtful way, easy to understand. Thank you.
Thank you. Thank you for the kind words. Appreciate it. Question?
Okay, so I've always been a fan of aperture fever,
Yes.
and I could never have a big enough telescope. So I'm wondering what's next in the concepts of, taking that next big step and finding even, getting closer to the origin of Big Bang and just about anything. As far as a space telescope,
Yes.
not a ground telescope.
I know that the Nancy Grace Roman telescope will be launched soon in a few years. That's also visible to, I believe, infrared light. I need to learn more about that. I know it's going to be a much better imager than Hubble was, and also it's going to be able to take a much bigger chunk of sky than James Webb did. So that may help. Again, I don't know enough about to really answer your question.
But not exactly what I was saying. How big is practical? What
Well,
can they do up there
oh, so okay.
before it becomes, impossible or?
Your biggest limitation is the launch fairing of your rocket. I suspect Webb is probably reaching that limit. However, what you could also do is build it in space. That would be the best way to go if you want to get gargantuan. The other thing to do is go to the far side of the moon and do an Arecibo-like setup in a crater. They've talked about that. That would work really well too. I hope so. Now, you're not going to get the infrared you want because the moon has its own heat, but you can get radio. You can also get, visual as well. They have talked about, and this is again right now just on paper, I think they call it the Carl Sagan Observatory, where they want to figure out a way of unfurling even a more massive mirror. So, I mean, why not? Maybe the engineers can come up with a solution where you can unfurl a mirror versus having a more mechanical setup like this. I would love to see that. I would love to see what they could figure out. It's actually give them a few $1 million and say, go. Money well spent. Other questions? Happy to answer them.
Yeah, Mike, so you can get rid of your 32. Yeah, you don't need it anymore. Any other questions for Michael? Excellent presentation. Let's
Thank
give him
you.
a round of applause.
Thank you. Thank you. Thank you.
Thank you so much, Michael.
And thank you for hosting. I'm glad to be here.
Okay, we just have a few announcements and we'll draw it to a close here. Eric will change slides here. First, there's a lot of crazy stuff going on in the universe, in our world. Let's talk about some good news, right? Good news. Hey, Lhasa National Park is open.
Yes.
It didn't close, right?
Well, no, it did close. It did close.
It did close.
It did close, yeah. That's why we got kicked out.
But it didn't get, any of the fire damage.
No, it got
Yeah.
right up to the border, but no, it didn't.
So keep our fingers crossed. We'll get another invite to
Yep.
go back to Lassen someday.
I will keep the club informed. It probably won't be till next year because winter's coming.
Yeah.
But I am really tight with the staff up there, so stay tuned.
Okay.
Yeah.
Oh, very good, very good. Let's see, other good news, Jeff Baldwin's heart surgery was a success and he's recovering. Boeing Starliner made it back to Earth. A little fewer occupants than when it left, but I mean, we got it back. So anybody else have any good news?
I saw a funny meme on that where, it was the astronauts in space saying, I feel so sorry for all those, people on Earth stranded.
Yeah, we're stranded, right? Yeah. Okay, so let's do the announcements. Eric, thank you for preparing the slide. Let's do it by category. So let's take the star parties first. Coming up September 28th, Highway 4. We're talking about doing the club potluck.
We don't have anybody that was really gung ho about getting up there.
Well, that's when we were talking about doing it at high altitude.
So
Is anyone here interested?
that's why I left it up there.
Yeah, I might be. Yeah. So I tell you what, everybody stay close to the Google chat line, and a week or so ahead of time, we'll start discussing it, who's going, whether we want to make it a potluck, what the weather's going to be looking like. So, okay, so
I
that's,
think you should kind of set maybe like a limit of how many people you think warrant a potluck. Just a recommendation.
If three people want to go out there and do a potluck,
Well,
they can do a potluck.
Okay.
okay, and then next star party I see is October 26th. Another Highway 4, November 2nd, high altitude, weather permitting, obviously. And all these dates are on the club's website calendar page, right? So you don't have to try to memorize all these dates. Okay, so that's star parties. And then general meetings coming up, October 10th. We've got a really good speaker. I'm really excited to hear Jacob Bivon. He's a PhD candidate from Bowling Green University, going to talk to us about his newest data that he's received from the Chandra X-ray telescope and his study of X-ray emitting binary stars. So put on your thinking cap for that one. It's going to be some deep science there. But that's October 10th. And then going down to November 14th, Eric's got this gentleman, Robert Douglas. He has this book. I'm really interested in hearing this, The Astronomical Curiosities and Explanation of Celestial Phenomena. Does that sound like a good program or what, huh?
He also has done some viewing from Australia, so he might be talking about what he's seen there and experiences there from Australia.
Yeah. Okay, so that's star parties, club meetings, and then I'm gonna hand the microphone to Doug and you'll cover public outreach, right?
So then that will be October 11th will be the next night at Delta College.
So we're back at Delta College now.
We're back at Delta College. We had about a dozen or so people come out.
Very
I think it was a little more than that.
It was a
More
little
like
more than
around
that?
30 maybe.
Okay. So it was a pretty good night. We can use, if Eric's gonna make it, I'll make it. And we can use a couple more scopes if anyone else could make it. Astronomy in the Park, October 12th. We had about 125 people on Saturday night. So we really need scopes out there. So all scopes. Once again, November 8th, back to Sky Tours. Okay, and November 9th, once again, we need a whole bunch of scopes out there. So if you can make these nights, please give me an email and say I'll be there. So that I know we got backup. Let's see, and then November 14th, So we still need a couple of members at large. Tim has said that he will continue as president. I'm willing to hang in as his second. Eric's willing to stay as secretary, and Jerry's willing to stay as the treasurer, although I think all of us wouldn't care if somebody wanted to take our jobs. You know, all yours. But we do need two members at large. So I thought, I heard that Casey was going to.
Nominate somebody?
Here you come in.
I thought Casey, I was gonna nominate Casey. That's where you describe the member at large role.
Basically, it's sitting in on a Zoom meeting on Thursday night, and giving us your 2 cents.
Mainly, we need to fill the positions so that we have a quorum, so when we
Yeah.
want to vote on something
Right,
that we want to recommend to the.
like I said,
the general society.
it's generally speaking, it's 2 hours on the first Thursday of the month.
And
If you can do-
we usually meet at 7:30 though, not 6:30.
Zoom.
Okay.
Yeah, and it's just by Zoom, so
At 7:30.
at 7:30.
I think I can do that. I just have to look at, I honestly
Okay.
have to look at my work calendar
All right,
as well.
Good job.
Can you-
Thank you.
Yeah.
email us back, please.
Yep.
But we likely need two, Casey.
But I heard we got a second.
I'll double check with Omar. And if not, we're just going to Shanghai Mike.
Yeah. Hey, Eric, go back a slide.
Either one.
It's better looking.
He looks like he put up a fight. I think.
Well, I can tell you stories about sadness, believe me.
Yeah.
I'm sure you have the same problem in Sacramento.
Yeah, we had quite a tumultuous year last year. Yeah.
So that guy wraps up our announcements. Eric gets photo credit for his photo of the moon.
Great job.
Eric, what can you tell us about that?
Basically, a minimal moon is when you sort of pull the color data out of the image like that. You normally see the moon grayscale, and so you can see a little bit of the reds and blues in there. And so that's really what it's referring to. This is-
It comes referring to element, I mean, like.
Yeah, there's
actual-
yeah, exactly. You got it.
Hey, Eric, how did you take it?
I took that with the C-Star S50 Smart Scope on video mode. I took about a 5-minute video, then converted that video with some stacking software, like that 50% of the best frames in that video. Stacked them, and then did the color bit in Affinity Photo. And you can use Photoshop, you can use GIMP, you can use other programs without this overnight. Yeah.
Great photo. Thanks. Okay, I have a couple of thank yous. I've been under the weather and Doug has been covering a lot of my duties. So thank you, Doug. And I don't know that some of you don't know this. So the reason we have this great meeting spot is because we have a quid pro quo situation with the San Joaquin County Office of Ed, where we support their Sky Mountain Science Camp, the kids' science camp up in the mountains. We support their astronomy program. And so every month, Jeff Baldwin had been sending them, what's up in the night sky. Yeah, so that they can go out and do some observing. With Jeff being out, Eric has pinched hit and taken care of that. So thank you, Eric, for covering that.
One, yeah, he already did September, but I'll do next month.
Okay, great. Jerry's not here, but Jerry's been successful in getting our bank accounts moved over to an interest-bearing account. So now we're earning money while we sleep. You like the sound of that?
Yeah, we already made $50 in like a month.
Yeah, it's pretty good. So Thank you all. And Michael, again, thank you for coming down. Great presentation. And with that, I'll just ask if there's anybody else have any comments or as we close the meeting.
Yeah, just real quick, you mentioned Sky Mountain. If you're curious, they recently put photos along the wall here.
Yeah.
So you can walk down and see some of the kids up at the mountain.
Oh, okay. Yeah.
Is there anything that you participated in actually going to as well?
I've been up there, but not.
Yeah, maybe Jeff and Ed Ribel have made trips up there in the past
Yeah.
to like scout the location and we gave them a scope. They have a scope.
I'd just like to thank Mike, you and your wife, because I desperately needed a brownie tonight.
Oh, yes.
You know,
You rescued me.
same here. I left late from work. I didn't have a chance to grab anything to eat for dinner. That was, I grabbed it. I didn't want to have a blood sugar collapse. In the middle of the presentation. Thank you. Very appreciated.
Yeah.
Plenty more, eat all you want.
Thank you, Mike and Susie. With that, let me conclude the meeting and adjourn us. So thank you all for being here.
So I know when after when I can start lifting things, just like that. Yeah. And walking.
Yeah, comes out to Oak Grove, Highway 4.
Shooting stuff out in every direction, but.
That's, it's a second part of that shape. I'm not quite sure why.
Yeah.
But it is. No.
Gravity's coming in. I guess, I just thought that energy coming in.
No.
We bounce back in other ways.
He's got that accretion disk.
Right, but I'm saying gravity's taking over. It's not a photo smart yet.
No.
Throw stuff out, I understand. That.
So yeah, it's all thermal energy because it hadn't lit the nuclear furnace yet.